Thank you very much. I'm pleased to be able to present recent achievements of our team at the University of Düsseldorf in here. My name is Soroosh Alighanbari. That was not so bad pronunciation of my family name. Well, now after Vladimir and Charlotte and Hugo's talk, we are all experts in HT+, so I can skip a bit faster my introduction part. Nope, wrong. Yes, now. Of course, Charlotte very well explained. I just add a little bit comment in here that determination of fundamental constants, test of theory, and search for new physics, possible new physics are interrelated in here. So we can do one at a time. And then on your comment on the, where is it here? On the electric quadrupole moment of HT of deuteron, we have already reported our result. It's a bit old, it's like 2020. I am not reporting it here, but I think our result is in agreement with D2+. Yes, please give me a comment.
So your result is in agreement with the determination from the D2 spectroscopy?
Yes, yes.
Is more accurate?
No.
Okay, thank you.
You are still safe. So I have it somewhere if you are interested, but it's a bit old. This is why I'm not reporting on it. Hugo already well explained it, but just briefly, of course, HT+ has electronic degree of freedom. Here you can see ground and first excited state. It has vibrational degree of freedom, and it has also rotational degree of freedom. Vladimir Korobov very well explained the spin-spin and spin-orbit interaction. And then I can hear myself. Okay, and in principle, this introduces a hyperfine structure for the row vibrational transitions. Small note here, of course, if you have a finite magnetic field here in unlike Penning trap, we have on micro Tesla level magnetic field in principle, then existence of magnetic field will remove what is happening. Okay, we'll remove the Zeeman degeneracy, and if the experimental precision allows, we can drive the transition between individual Zeeman components. The challenges for precision study of molecular hydrogen ions in total and HT+ as a special case has two sides. On the experimental side, of course, for both of them, the goal is to achieve the highest accuracy. On the experimental side, you have to get rid of the Doppler broadening. Long observation times are required. We need to have a good control of systematics. We need to resolve hyperfine structure, and also to reach to the ultimate goal, we need to measure several transitions for at least two of the isotopologues. On the theory, of course, three-body Schrödinger equation and Dirac equation are Dirac equation for electron, I think, bound to clamp nuclei, if I'm correct here, are exactly numerically calculated, but it's not sufficient. We need higher order QED calculations. And in principle, the hyperfine structure theory is not necessary if we can resolve all of the hyperfine transitions for our row vibrational spectroscopies, but in practice, we need them. At today's precision, both theory and experiment are at PPT level. So far on HT+, I think there are just 5 spectroscopy results with experimental uncertainty smaller than the theoretical uncertainty. So there's a lot of room for improvement and for further interrogations. Our method to overcome the experimental challenges is relying on the Decay's suggestion. In 1953, Decay suggested that if our quantum system has extent of motion delta x and it has a transition wavelength lambda, if lambda satisfies this equation, in principle, we expect a Doppler-free profile. How we do that? We normally load a large cluster of beryllium ions inside our linear pore trap. We use cooling laser cooling method to decrease the temperature of the beryllium cluster to around 10 millikelvin or even lower. And in principle, simultaneously, we trap HD+. Due to the smaller charge square to mass ratio, larger charge square to mass ratio of HD+, it will stays closer to the trap axis. And if we send our spectroscopy laser transfers to the trap axis, and if the wavelength is larger than the extent of radial motion of HD+, we will be in the lambda regime or decay regime. Here you can see a CCD image of our large beryllium cluster, and here in the center there is a string of HD+ molecules. Our detection scheme is, as Charlotte explained already, is destructive. What we do is that normally after deriving the spectroscopy transition, we dissociate the molecules from the excited states. And in principle, by comparison of the number of trapped HD+ after and before this dissociation, and looking at the relative loss of the HD+ molecule, we get the relative strength of our signal. On the other side, unlike penning trap, which is at 4 Kelvin also, our system is at room temperature. So there would be a thermal distribution of the population between the ground rotational level, between the ground vibrational level. And to overcome this problem and increase the population in the ground state, which is the goal state for our spectroscopy, we use a laser rotational cooling. We drive these two transitions, remove the population from the from N1 and N2, and then through the spontaneous decay, we will increase the population in the ground state. For our spectroscopy, of course, we need ultra narrow, ultra stable lasers. Our method is to phase lock frequency reference our lasers into an ultra stable frequency comb. We also use nonlinear optical frequencies to produce ultra stable radiation at for mid-infrared range, which mid-infrared range, which is required for HD+ spectroscopy. We have performed a molecular dynamic simulation of a cluster of beryllium and HD+ for temperatures around 10 millikelvin. Our simple model shows that the radial extent of motion of HD+ is smaller than 2 micron. So this means in principle, it is not so risky to drive the fundamental vibrational transition at 5.1 micron. By doing that, we achieve Doppler-free profiles with full line width as low as 130 hertz. Of course, here the natural question is that how far can you reduce the wavelength of your transition and still have the Doppler-free profile? We pick a little bit brave step forward, and we went to fourth overtone transition at 1.1 micron, and surprisingly, we still have a Doppler-free profile. Why surprisingly? Because in principle, it is not predicted by our simple model. Simulation, but still not predicted. Possible explanation is that there is a transient decay regime, that there are finite intervals of time that the extent of motion is smaller than the wavelength. And this ends up to have a Doppler-free profile, and then other intervals of time, it is just a broad, weak Doppler background. With this measurement, we achieved line width as low as 340 hertz. Our Q factor is the highest Q factor for any molecular ion spectroscopy, and it is close to the highest Q factor achieved for strontium-2 molecular optical, the neutral strontium-2 molecular optical clocks. Another observation that we had is that we observe a frequency discrepancy of 50 kilohertz between our experiment and the predicted theoretical frequency. In principle, this shift is equal to the recoil shift induced by the spectroscopy laser. To achieve our goals for this spectroscopies, we of course need to experimentally investigate and determine the systematic shifts, the known systematic shifts. Here you can see our error budget for one of the hyperfine states. We have measured for fundamental vibrational. The other hyperfine has the similar error budget. Okay, now we can test the hyperfine structure theory. for fundamental vibration and fourth overtone transition, we measured two hyperfine transitions. In principle, we can determine the hyperfine frequency difference experimentally. And as you can see here, we have a good agreement between theory and experiment within the combined uncertainty. I hope Jean-Philippe Carr is not going to ruin my happiness with this, because we are waiting for his result. Let's see if there is a discrepancy also here. But unlike the rotational and the ninth overtone transition, I think we are using your current numbers, like E1 and E4 and E5 are from your recent publications in these theory values. So this is in principle, well, obviously the experimental uncertainty is smaller than theory. And this is the stringent test of hyperfine structure prediction for HT plus at the level of 2 × 10⁻⁵. We can also test the correctness of QED calculations by comparison of the spin average frequencies. So we use a combined frequency approach. We have this weight factors B1, 2. We choose them such that we minimize the spin theory uncertainty. Using this, as you can see, we find a good agreement between experiment and theory. Unfortunately, the largest uncertainty on the theory side is coming from the values of fundamental constants, CODATA 2018. This is in principle this is the test of QED calculations for bound three-body systems at the level of 2 × 10⁻11, but of course it is limited by CODATA uncertainties.
This CODATA uncertainty is the electron-proton mass ratio.
Mass ratios, nuclear charge, radii, and Rydberg constant, because all of them are there. On the QED calculations, yes, I will show it. So these achievements, in principle, now I'm just explaining these two last measurements, are 2 to 5 orders of magnitude improvement compared to our old measurements. On the nuclear charge radii, you have seen the proton radius puzzle. Of course, the full picture, I just put a selection in here. Our spin average frequency, of course, also depends on the value of the proton and neutron charge radii. For the fourth overtone transition, as you can see, we have a shift at the level of 73 kilohertz and 465 kilohertz. So we are sensitive to the proton and neutron radii. In principle, if we, for spin average frequency, the theory value, we use the CODATA 2014 fundamental constant, we will have a discrepancy of 21 kilohertz between theory and experiment. So this means our experiment is consistent with CODATA 2018. But unfortunately, the total uncertainty is quite large, and we really cannot competitively contribute on the proton radius puzzle at this point because of the large uncertainties. Okay, like now let's consider that the theory is correct, the experiment is correct. Now we can determine value of a fundamental constant combination. So mu is the reduced nuclear mass ratio to electron mass. We can use individual results and then use the theory experiment comparison. Of course, we need them to get the nuclear charge radii and Rydberg constant from CODATA. Then we can determine the mu over me. Or we can use least squares adjustment to adjust the value of mu over me using all of the 4 previous measurements. Here, as you can see, from individual frequency measurements and also least square adjustment, we find a good agreement between our data and the value from CODATA 2018. Also, within the combined uncertainty, we find an agreement between Penning trap measurements and also our result. But as you can see, our uncertainty is smaller than CODATA 2018. We can also use the proton-neutron mass ratio measured directly with the Penning trap mass measurements to determine the value of the proton to electron. Our value is in agreement with Penning trap mass measurement, but it has a little bit smaller uncertainty. Okay, now if we consider that theory is correct, fundamental values are correct, and then we try to search for physics beyond standard model. We can imagine that there is a hypothetical interaction between proton and neutron, and existence of such interaction will change the molecular potential. And that change in the molecular potential will change the transition frequency. For our test, we consider a Yukawa type interaction between proton and neutron with strength beta and for a range of interaction lambda. In principle, here you can see the sensitivity of the individual transitions. And of course, here are the ratios of the frequencies to such a Yukawa potential for 1 angstrom range or something like that. In principle, we can set bounds from individual experiment theory comparisons, or we can also set a bound from a least square adjustment to beta and mu over ME for each of the interaction ranges. As you can see here, our least square adjustment improves the limits set by previous individual experiment theory comparisons. Of course, for the full picture, what we need is to consider the free fall between all of the particles, not just the nuclei, but also electron and baryons and the nuclei there. As you can see, the sensitivity of the transition is calculated for the Yukawa type potential. Of course, the desirable would be that we have a full analysis based on not just Hd+, but also hydrogen, deuterium, and probably other isotopologues of molecular hydrogen ions. We have also tested the Weinberg's quantum mechanics extension. Weinberg suggested that there is a possibility of observing small deviations from ordinary quantum mechanics implied by the Lindblad equation. He suggested to do the energy closure tests. In principle, we can have a 3-body system, a 3-level system. We can drive these 3 transitions. In principle, these transitions can be measured experimentally and also computed theoretically. The energy closure says that the summation of frequencies should be the same, but not the deviations. So in principle, we can use Hd+ or theory. And here, as you can see, for 4th overtone transition and for the comparison of the ratios of F9 and F5, we didn't find any effect so far. For the outlook, of course, we need to measure hyperfine components, more hyperfine components, and increase the experimental accuracy. We can use single molecular ion trapped at the same time with a single beryllium. This is a work in progress in our group. My colleague is working on it, and we have already observed a first vibrational excitation of a single molecular hydrogen ion. Of course, the ultimate goal is to do the precision spectroscopy of homonuclears to directly determine these fundamental constants. Flexible approach would be to use the E2 transitions, for example, here for H2+. As a test case, we use a 2 transition for Hd+. First, we use the axial excitation, achieving a line width of 2 megahertz, and then we use our TIC-TES method. And now we have observed the first Doppler-free E2 transition for molecular hydrogen ions. This is 40,000 times improvement compared to the previous results. And by this, I can give you the summary. We have used our TIC-TES method for Doppler-free 1-photon spectroscopy of molecular hydrogen ion Hd+ here. Our results are 2 to 4 orders of magnitude improved compared to the previous, and the fractional line width and experimental uncertainty are at PPT level. We have tested the QED theory and also the hyperfine structure theory. We find good agreement between theory and experiment. We determined the value of fundamental constant mu over ME in agreement with CODATA 2018 and Penningtrap. So far, we didn't see any effect as suggested by Weinberg's hypothesis at the current uncertainty. We observed the first E2 transition for a molecular ion, and we have also improved the limits for existence of hypothetical forces between proton and neutron. I would like to thank my colleagues at the University of Düsseldorf, Laurent Constantin from Lille, and of course, Vladimir Korobov and Theory Weiss, with whom we have long-standing collaborations. Thank you very much.
Thank you for presenting excellent results. There are many questions, so please be patient. Everybody will be able to ask questions. We'll be delayed by an hour, but questions are more important.
Yeah, absolutely amazing results. Thanks a lot. First a comment and then a question. First, what the comment is, forget about co-data. It's political values. So if you want to have a Ripper constant and charge radii, you take the muonic charge radii and the corresponding Ripper constant from 1s, 2s in hydrogen deuterium, right?
Oh. Tell him.
Okay, the second, well, half joking, but certainly I would be very astonished if these two were wrong on our level of accuracy. And the second one is, how long does it take you to measure one data point? And how do you produce the error bars in your resonance spectra? Because for me, it looked like these error bars are very large compared to the scatter, and they are all, within less than a sigma or so of the fit function.
Yeah, so as I said, we have this destructive method. So in principle, let's say this point is what we do is that we load HT plus, we drive the transitions, whatever is involved, and then we dissociate it, and then we compare the relative loss of the ions. And that would be one point, for example, when the frequency of the laser is 8 kilohertz in this scenario. Then we have to measure it many times. And when we do that, in principle, we collect with some uncertainty the relative number of dissociated molecules. And that makes our mean and standard deviation for one point. This is how we measure it. It's the standard deviation of the mean, yes. Oh, sorry, standard deviation of the mean, yes. Yeah.
Yeah,
same thing.
Same thing. No, but I asked you this question at the previous meeting.
Yes.
But there was. My question is, I didn't quite think it was a great talk. I didn't quite understand your point about the sums and differences when you were talking about the Weinberg nonlinearity.
Yes, because like I thought that I'm like running out of time. I just like fastly went through it. Where was it? Okay. So in principle, now I have a bit more time to explain it. So in principle, there is a departure, which is this curly E, that is different, can be the difference between computed transition frequency and measured transition frequency. So in principle, this E here is just measurement minus experiment. And then the coefficients that these ratios that I am saying is just the difference between theory and experiment divided by experimental transition frequency. And then, of course, this test can be used just for calculable quantum systems. Of course, HT plus would allow us to test, because it has also, like, we can also drive this transition, and then we find a closed three-body system and then compare it directly by observing this possible departures.
Okay,
Yeah, about this issue, about you had this triangle, yeah, that you were testing, three transitions.
Yes.
But if you use dipole transitions, this doesn't work. I mean, then the parities don't match in the triangle.
Well,
then if you want to test a triangle fitting a consistency of three transitions, then they do. I mean, you start from a certain parity, you go up to parity, and then you go up to that one, and they're not connected. So then you cannot test this triangle consistency.
It's just
look, there's a comparison. So if I was explaining, one can drive this transition anyway. This is what you want to say.
on the HT plus, you mean? Okay, yeah, of course. Then we can use like one of them at E2 transition and the other ones at yes, I'm sorry. But anyhow, it is not forbidden. It's allowed. We can do it.
Okay, pass the microphone here.
I think I misunderstood your questions. I'm sorry.
So maybe a more technical question on the ion trapping. So I was a bit surprised that you have no Doppler broadening, but you have a recoil shift. So how does that work? I thought in the Lambdicke regime you have neither. So
yes. Okay, okay. So there is a small difference between our system and let's go up to that plot in principle, because then I can explain it here. So that's in principle we have opposite limit to single ions or two ions. So in single ion or two ion systems, in principle, the secular motions, the motional sidebands, the mechanical motional sidebands are easily kilohertz away from each other, and then you can easily resolve the carrier, right? Yes. But in our case, we have a large cluster, and it has a lot of mechanical degrees of freedom. Unbelievable, some of them are even just few kilohertz from each other. Mm-hmm. So you will have like a big overlap of all of them. And in principle, on general grounds, I would say those sidebands will produce this recoil shift.
But then it's amazing that you don't get Doppler at the same time, Doppler broadening at the same time, right? Because it's kind of the same effect. So it
is possible that they are like all of them cramped in this range. Okay, one thing is that we didn't continue to see how many sidebands we have.
But at 1 millikelvin, you should get a much broader Doppler width than that, right? So it's weird that only the recoil shows
yes,
up.
Yes, but then 1 millikelvin is restricted by the fact that you have the extent of motion smaller than the wavelength. So unfortunately, I do not have the decay suggestion plotted here, but decay suggests that if you look at it, it has like a Doppler broad profile background, which is lost into our background noise, unfortunately. We cannot see it, and a Doppler on top. And probably that's what we see. We see that tiny Doppler on top of that very broad Doppler broadened background.
Okay, yeah, thank you. Interesting regime. Yeah, it's a bit unusual.
It's a bit unusual, yes. It's a bit unusual.
Further questions?
Another practical question. So you have many transitions that you can access. Why choose the infrared? Is because of the Dick broadening, the Dick narrowing? Why don't you go to some other?
Like what? Like okay.
I mean,
here's the point. Here's
so
the point.
many
Okay.
levels.
That's exactly. Sorry. Yes. No. It's correct question actually. So that's exactly what. This is what we want to do. We want to have a. I have to show this one. We want to have a lambda which is larger than delta x, right? Okay, so just imagine that for single ions, it's a different story than the string that we have. Okay, the string that we have has small extent of motion, but our simple model and simulation shows that it is smaller than 2 micron, right? So when it's smaller than 2 micron, of course, you cannot drive a transition at 532 nanometer, because I think like 1.1 micron is still extremely surprising for us. But first of all, if you don't have any, at this point, I do not have any laser to investigate like larger overtones, like whatever delta V equals 9 or something, but I do not expect this works.
But you could use like 2-photon transitions or other things.
That's already happened in Amsterdam group. Okay, this is one of the very recent measurement 2022. This one.
Amsterdam group is a next talk.
That's the next talk. They
cool.
will. Yeah. Where is he? Yeah, somewhere there.
Well, okay.
Thanks for the very nice talk. I have a question about the fifth force.
Yes.
In the formula you describe the fifth force, there's no spin in the formula, right? But
yes.
In the end of this slides, you said it's the spin average, the fifth force.
Yes.
So how
so
come?
it means there is no spin there. Okay, spin average in principle is where is it? Here. Spin average in our case is which means simply we just look at the QED and Schrödinger equations, right? So we do not look at the hyperfine structure. And this is how we use it. So in principle, we do not have hyperfine structure. If you want to consider fifth force, hypothetical fifth force with spin, you have to consider hyperfine structure and then compare hyperfine structure transitions between hyperfine structure with theory. But their uncertainty is not so good. Right? At the level of 10 to minus 5, so it's not really so.
If the molecular is spin polarized, is that possible? Or in this experiment, it seems it's not spin polarized, right? But can people do this spin polarized? I mean, the whole ion is spin polarized, or
it is possible. As I said, it's not impossible. It is possible to search for spin-dependent hypothetical forces. The only thing is that at the current resolution, precision, it's really not so meaningful, because as I showed you, like we are at the level of 2×10⁻⁵ for this hyperfine structure. So both.
Try to squeeze the answers.
I'm sorry. So we need to read. Oh yeah, I'm running out of time.
But there are more questions. Ben.
Okay, super fast. Don't you have off-diagonal hyperfine, which will affect the average?
No, I don't think so.
It's a good question for this hyper-averaging. Means, let me say, personally, I don't understand hyper-averaging, but it's a very good question, because it has been questioned by your coworker. I forgot. I cannot pronounce his name. In your laboratory, he has written a paper. No.
Kulemay.
He has written a paper about. He questioned this spin average. So it is something to think about.
I mean, there are some off-diagonal element of the hyperfine Hamiltonian coupling J=1 and J=3 in hydrogen molecule, and that will be the same also in HD. And that is correct what you say.
As I understand, they diagonalize. It means you should answer, because once you have all the coefficients, you diagonalize the effective Hamiltonian and find out all the levels. Or maybe, I don't know. So this was the reason of this Kulemay paper. Gordon, you would like to ask a question?
On the question of averaging, you get the same thing with the fine structure splitting of the triplet P states. You have off-diagonal mixing with the singlet P for J=1, so you get a shift in the center of gravity.
So we all of us remember the discrepancy for hyperfine splitting Karobov. It was small discrepancy of 10 sigma, and something is missing. And we don't know what. Let me thank you once again for excellent talk. Impressive talk.
Thank you.